Hey students, this is a video on partial fraction decomposition. Now, partial fraction decomposition is technically a topic from pre-calculus, but most people haven't seen it before. It's not commonly covered, at least not in the pre-calculus that's offered at Merced College. But it is a very important technique, and the reason we're learning it is later in another video, I'm going to show you how to use it to actually be able to calculate some integrals that you wouldn't be able to do any other way. So now partial fraction decomposition, what decomposition means is to break up a whole into little parts. And the basic idea is you're going to have a single fraction, and then when you do a decomposition, it breaks into multiple fractions. Okay, so it'll become two or more fractions. So we're going to go through an example here so you can see exactly what I'm talking about. But basically, you take one fraction and you split it up into two or more smaller fractions. That's basically what decomposition means. Okay, so example. The instructions on your first part of your homework are going to say, find the partial fraction decomposition. Okay, find the partial fraction decomposition of each rational expression. Okay, so for the rational expression. For the rational expression. Now remember that a rational expression, the word rational is built from the word ratio, which basically means fraction. Okay, so when they say rational expression, they mean you're going to start with a single fraction. So that's what the rational expression is. Okay, so you start with a single fraction, and then the decomposition actually means you split it up into multiple fractions. So you'll either split it up into 2 or 3 or even 4 fractions, which are going to be less complicated than the original one. But it's been decomposed into parts. Okay? So yeah, decomposition means split into multiple fractions. Okay? Split into multiple fractions. All right, so that's a basic idea there. And that's just the words behind it. So let's see an actual example. So for our first example, for example number 1, we're starting with the fraction, which is 9x plus 29 all over x plus 3 times x plus 4. Okay, so 9x plus 29 all over x plus 3 times x plus 4. Okay? Okay, so what are we going to be doing with this fraction? Well, like I said, we're going to be splitting it up into smaller fractions. But then the question is, what are those smaller fractions going to look like, and how do we know how many of them there's going to be? Well, you look for the number of distinct factors in this denominator. That's actually the trick there. Okay, so looking at this denominator, we can see we have 2 distinct factors. So you have 2 factors here. When I say distinct, they're different. So distinct means they're different. So x plus 3 and x plus 4 are different factors. So what the right side is going to look like is it's going to be, we're going to write a capital A as an unknown. Okay, so we're going to have capital A over the first factor, so capital A over x plus 3, plus capital B over the second factor. So that's going to be capital B over x plus 4. Okay, so once again, what we have here is, because there's two factors here, when we split it up into fractions, we're going to get it as each of those factors. Notice that in each denominator, I have one of those two factors. So if there had been three distinct factors, we would actually have capital A over the first factor, plus capital B over the second factor, plus capital C over the third factor. Now, capital A, capital B, capital C, those are all unknowns. Okay, so when I say unknowns, that means we're going to have to solve for them as we're doing the problem. Okay, so capital A and capital B are both unknowns. Okay, those are unknowns. But the whole goal with partial fraction decomposition is just to be able to split up a complicated fraction into single fractions that are simpler. And as you can imagine, if you're doing an integral and you have a complicated fraction like this, if you split it up into simpler fractions, then those will be easier to integrate. Just because when you're doing an integral, if it's a less complicated fraction, it's more likely that you're going to actually be able to do it. You're going to actually be able to integrate it. Okay, so that's the basic idea. So you look at all the factors in the denominator, and then each one appears in a separate fraction on the other side, and then you're adding those fractions together, and you have unknowns in the numerator. Okay, and because these factors were linear, both of these factors were linear, that means they don't have any powers. We ended up with just two fractions. So as long as they're linear, you can just do what we did here. It's the easiest case. Okay, so now you might be wondering, well, that's great, but how do we find A and B? Well, how do you find A and B? Well, notice we have an equation now. So with this equation, what we can do is we can actually multiply both sides by the LCD, but that confuses some people. That's how they do it in our book, but it confuses some people. So another way of thinking of it is you can build each of these fractions on the right side so that they have the same denominator as the left side, and then you can cross out all the denominators once they're all the same. Okay, so in other words, what I'm saying here is we build each side to the same denominator, just the same way you always do with fractions. Okay, so that's what we're going to be doing here. Build each fraction to a common denominator, or to the common denominator. I should probably say a common denominator. So most people would build them to the LCD. Sorry, my pen's messing up right now. Okay, there we go. Okay, so build each fraction to the LCD. And the LCD literally just means you build each fraction so that it has the same denominator. That's all it means. Least common denominator means it's the simplest one you can find. Okay, so here on the left side we have an x plus 3 and an x plus 4. On the right side we're going to need to multiply each of these fractions on the top and the bottom by whatever we're missing. Okay, so what are we missing over here? Well, in this first fraction we do have an x plus 3, but we're missing an x plus 4. So we're going to need to multiply this one by x plus 4 on the top and the bottom. Okay, so if I rewrite this down here, on the left side we're already good. On the left side we already have a common denominator. We have a complicated denominator. We have x plus 3 times x plus 4. But on the right side we need to multiply each fraction by whatever we're missing. So what we're missing on the right side there, in the first fraction, is we're missing an x plus 4, so we're going to multiply that by x plus 4 on the top and the bottom. Okay, so on the top we have a times a quantity x plus 4, And then on the bottom we have x plus 3 times x plus 4. So as you can see there, actually let me do that in green just to make it a little bit more visual. I almost forgot about the whole idea of doing it in different colors just to make it visual. So here we're multiplying this term right here by what we're missing. So we're multiplying by x plus 4 on the top and the bottom. And remember, you have to multiply both the top and the bottom by the same thing. Otherwise, you'd be changing the fraction, which you're not allowed to do. Okay, so we're building these all to the LCD. And then the other term on this right side is b over x plus 4. So we can see what we're missing from this denominator is actually an x plus 3. So we're going to be multiplying this fraction by x plus 3 on the top and the bottom. Okay, so we have plus b over x plus 4. And then we're multiplying the top and the bottom by x plus 3. Okay, and after you've built everything to the LCD, then what you can do is, since they all have the same denominator, you can just multiply both sides by the LCD, which gets rid of all the fractions. Okay, so we built each fraction to the LCD, and then what we do is then we cross out all denominators. Because all the denominators are the same, which means you can multiply both sides by that denominator. Okay, so for the fractions, we've already done the hard part, which is building them to the same denominator. But now that all these denominators are exactly the same, we can see each one of them has x plus 3 times x plus 4. Remember, the order doesn't matter when you're multiplying, so this last denominator is actually the same thing. It's just the order switched around. We can cross them all out. In other words, if we multiply both sides by x plus 3 times x plus 4, every single one of those denominators cancels out. So what are we left with? Well, on the left side, we're left with 9x plus 29. And then on the right side, we have a times the quantity x plus 4 plus b times the quantity x plus 3. Okay, a times the quantity x plus 4 plus b times the quantity x plus 3. And then what can we do from here? Well, actually we've done the hard part. Well, a lot of people don't like fractions, so now we don't have any fractions left over, which is nice. So what we do next is we go ahead and we distribute the a and the b on the right side. Okay, so we're going to go ahead and distribute the a and also distribute the b on the right side. Okay, so what's that going to give us? Well, on the right side we have ax plus 4a, and then we have plus bx plus 3b. And on the left side we have 9x plus 29. Okay, and then what can we do from here? Well, it turns out that you can equate the coefficients of like powers of x. Okay, so let me write that down. Equate. So what does the word equate mean? Equate means set equal to each other. Okay, so equate the coefficients of like powers. And remember, like powers just means you have the same powers. And when I say that, I mean on each side, okay? So on each side. So what's that going to look like? Well, With this one, we're looking at x because x is our variable. Remember, capital A and capital B are unknowns, but they're technically not variables because you're going to actually solve for capital A and capital B, so we're going to find out what they are at the end. So what are the like powers here? Well, first of all, we have the 9x, the ax, and the bx. So what does that look like? Well, I highlighted them in blue. Just equating the coefficients, not the actual x's, we're going to get an equation. So on the left side we have 9, and then on the right side we have a plus b. So we have 9 equals a plus b. See what I did there? I just highlighted the powers that were just x, the x power, which is x to the 1. So we have 9 on the left side, and then on the right side we have a plus b. Those are the coefficients of the like powers. And then what about the rest of this? Well, in green here I can highlight the constants. Okay, so here the constants are 29, 4a, and 3b. So on the left side we have 29, on the right side we have 4a plus 3b. So what's that equation going to give us? We're going to have 29 equals 4a plus 3b. Okay, 29 equals 4a plus 3b. All right, and then what do we do from here? Well, remember, a and b are unknowns, but they are not variables, so they're actually something that you want to solve for. And our goal at the end of this is once we know what a and b are, we're going to be able to plug them in back into this original equation up here, and then we'll have the right side of this equation, and that will actually give us the partial fraction decomposition, which is what we want. All right, so we equated the coefficients of like powers, and we got these two equations here. And these two equations are together form a system of equations. Okay, so we're going to go ahead and solve the system. Solve the system for each unknown. And I'm calling them unknowns because they aren't technically variables, even though we're treating them like variables. They're more like something that we need to find by the end of the problem, so we'll actually have numbers. So capital A and capital B are the two unknowns that we need to find here. And this is a system of equations, so you can either solve it through substitution or addition. There are two different methods. Or you could use a graphing calculator if you wanted to let a be x and b be y, but that's up to you. So anyway, here I think because they're already lined up, I think I'd like to do addition. So I'm going to multiply the top equation by -4, so that way when I add them, the a's cancel out. Okay, so if I multiply this top equation by -4 on each side, then the a's are going to cancel out. So my system of equations is now going to become, well, we have -4 times 9 is -36. So we have -36 equals -4a minus 4b. And then the bottom equation hasn't changed. So the bottom equation is still 29 equals 4a plus 3b. And I just multiplied both sides by -4 because I arbitrarily decided I wanted to cancel out the a's. But you could have also multiplied both sides by -3 if you wanted to cancel out the b's instead. Okay? So what we do now is we're doing the addition method. So now we're going to go ahead and add these two equations. And if we've done it correctly, one of the variables, or in this case, one of the unknowns, should cancel. So if I add vertically here, we get negative 36 plus 29, which is going to give us negative 7. And then on the right side, the negative 4a and the positive 4a cancel. And then negative 4b plus 3b gives us negative b. Okay, so we actually have negative 7 equals negative b. And of course, we can solve this for capital B by multiplying both sides by negative 1. Okay, so if I multiply both sides of this equation by negative 1, then that's going to give me b equals 7, right? Because the negatives cancel out on both sides. And so we get capital B equals 7. Now that's not actually our answer, that just means we solved one of the unknowns. But I said solve the system for each unknown, so in this case we still need to find A. So how do we find A? Well, now that we know what B is, we can plug in B into one of the original equations and solve for A. And the one I'm going to choose is the one up here because it has smaller numbers than the one on the bottom. All right, so I'm going to go ahead and plug in B equals 7 into the top equation. And I mean the top equation before we multiplied it by negative 4, because that's just simpler. Okay, so what we get is we get the top equation is now 9 equals A plus 7. Okay, 9 equals A plus 7. And then to solve for A, we can just subtract 7 from both sides. Okay, so if we minus 7 from both sides, we get A equals 9 minus 7, which is 2. Okay, so now we have A equals 2, B equals 7. But these are not our answers. This just means we've solved for the unknowns. So how do we write our answer? Well, actually, we're almost done. All we do is we plug in A and B into the original equation that I wrote up here. So this original equation, there's a train coming by. I'm going to pause it until the train passes. Okay, sorry about that. I just paused it and then the train went by. Okay, so anyway, as I was saying before I got interrupted by the train, basically all we're going to be doing is plugging in A equals 2 and B equals 7 into the right side of the original equation. And that's going to give us our partial fraction decomposition. Okay, so right here on the right side, this right here, we're going to go ahead and plug in our unknowns now. And that's going to be our actual answer. Okay, so we're going to have A was 2, so we have 2 over x plus 3. And then B we said was 7, correct? Is that what I just said? Yeah, B was 7, A was 2. So we're going to have plus B is 7 over x plus 4. Okay, so 2 over x plus 3 plus 7 over x plus 4. And this right here is our final answer. So I'm going to go ahead and box that. And that is a partial fraction decomposition. So what have we done? We've actually taken this original fraction, which was a single fraction, and it was a bit complicated, and we split it up into two smaller fractions. And some of you can probably already think in your head how this would be useful for an integral. Because if I look at this original fraction, this one could be very difficult to integrate. I'm not quite sure. There might be a way of doing it. If you multiplied out the denominator, you might be able to do it with u substitution, but you might not. Whereas what we've done here is there are certainly problems where you wouldn't be able to integrate the fraction. And in those problems, if you split it up into smaller fractions like that, Here, these are very easy to integrate. So like each of these would be giving you, if you integrated this, you would have 2 times natural log of x plus 3 plus 7 times natural log of x plus 4. So it's so easy to integrate, I can just integrate it in my head. So hopefully you can see the value of what we're learning. And we are learning it for integrals, but it does have other applications, such as in linear algebra or other kinds of math. Okay, so that was a relatively easy one where we had 2 linear factors. And now I want to jump ahead to a later problem in your homework, which is just a little bit trickier. Okay, and for our homework we don't get into the really difficult ones, but we do have a couple of trickier ones. So I wanted to show you one of those. Okay, so let's take a look at example number 2. Okay, example number 2. Same instructions, expand the quotient by partial fractions. Quotient just means a fraction. I guess the other one said a rational expression, but same difference. So what we have here is x plus 7 over x squared plus 12x plus 36. Okay, so x plus 7 all over x squared plus 12x plus 36. All right, and we want to expand this. Now, obviously, one thing that's harder about this one is right off the bat, our denominator is not factored. Okay, so that's an additional step that we're going to have to do first. And hopefully we can factor the denominator. If it can't be factored, you actually have more difficult problems than what shows up in your homework. But for us, we're in Calculus 2. We're trying to get the idea down, but we're not trying to jump into the really hard problems. Here I'm trying to give you an overview of the different kinds of problems. Okay, so what we're going to do here is, since this doesn't have linear factors, the highest power is actually 2 instead of 1 here. We need to factor. Okay, so factor. So how do you factor? Well, many of you can probably factor this one in your head, but if not, you can use the X method, okay, or the diamond method. So on the top you write 36, which is the third term, and then on the bottom you write 12, which is the middle term. And we want 2 numbers that multiply to 36, but add to 12. And that should already be popping up in your head. Well, 6 times 6 is 36, but 6 plus 6 is 12. So the winning numbers are 6 and 6. Okay, and then remember that's actually how you factor it. So it's going to factor as x plus 6 times x plus 6. Okay, so on the top we have x plus 7 still. On the bottom, now we've factored it as x plus 6 times x plus 6. Now something to keep in mind here is that for this denominator, these factors are not different, they're not distinct, which means you need to combine them together as a power. All right? So because these 2 factors are actually the same, we need to combine them. So instead of writing x plus 6 times x plus 6, we're going to write them as x plus 6 quantity squared. Okay? So what we got here is x plus 7 over x plus 6 quantity squared. Okay, and then and that's the beginning of the problem. Now the question is, how am I supposed to write this on the right side? Because on the last problem we had 2 different factors in the denominator, and we could see that with that one we were able to write it as a over the first factor plus b over the second factor. So what do we do here? Well, it turns out that if you have a linear factor like this, but it's raised to a power, you need to include all the powers starting from its power, and you count all the way down to 1. Okay, so what does that mean? That means here you need to have both a square power and then a first power. But what most people do is they actually start with the smallest power and then they write the larger powers next. Okay, so what we got here is we're going to have x plus 7 over x plus 6. Okay, that's x plus 6 to the first power. So I'm starting with the smallest power, which would be x plus 6 to the first power. And then we also need to write another factor. I'm sorry, not x plus 7. I was supposed to write a. Wow, that was quite a brain fart. I'm a bit tired. So anyway, what I was saying is you write it as x plus 6 to the 1. And of course, just like on the last problem, we want to write a in the numerator. Okay, so in the numerator here, we're going to have capital A, which is our unknown. And then for the second fraction, we're going to write capital B over, and this one is going to be x plus 6 to the second power. Okay, so we have x plus 7 over x plus 6 quantity squared on the left side. Because it had a second power, that means we need to have a first power and a second power on the right side. So basically, I started with the smallest power of x plus 6, which is x plus 6 to the 1. And then I increased until I got to the largest power, which was x plus 6 to the 2. Okay, and we're not going to be doing one with a cube, but I think you can imagine what it would look like with a cube. So let's say it was x plus 6 quantity cubed in the denominator. Then you would actually need an x plus 6 to the 1, an x plus 6 to the 2, and an x plus 6 to the 3. So it would be a over x plus 6 to the 1 plus b over x plus 6 to the 2 plus c over x plus 6 to the 3. But we're not doing cubes here, we're just doing squared in your homework, at least so far. So we're not going to worry about that yet. Okay, so that's how you do it when you have a power of a linear factor. So how do I say that in words? Well, write all powers of that linear factor. And remember, x plus 6 is a linear factor because the highest power is 1. This square is actually on the outside. Okay, so setting it up like that is the hardest part, but I think you get the idea now. Okay, and remember that x plus 6 to the 1 is the same as x plus 6. So I don't really need to write this 1 here. I just wrote it when I was describing the powers to you. Okay, so now that we have it set up the correct way, the rest of the problem is just like the last problem. So now we want to build each side to the LCD. So in particular, here we can see that the LCD is going to be x plus 6 quantity squared. So we need to multiply this first fraction on the right side by x plus 6 on the top and the bottom. Okay, so if we build to the LCD, remember LCD is the least common denominator. But it's still a common denominator. We can see that the LCD here is going to be x plus 6 quantity squared. So we go ahead and multiply on the right side by x plus 6 for this first fraction. So we're going to multiply this one. Actually, let me do it in green. We're going to multiply this first fraction by x plus 6 on the top and the bottom. Okay, so what's our equation going to look like now? Well, the only thing that's changing is this part right here, where we multiplied by x plus 6 on the top and the bottom. So the left side and the right side are going to be mostly the same. So we're going to have x plus 7 over x plus 6 quantity squared. Okay, so x plus 7 over the quantity x plus 6 quantity squared equals, and then on the right side, now we're going to have a times x plus 6 over x plus 6 quantity squared. Okay, so a times x plus 6 over x plus 6 quantity squared. Alright, and then we still have a b over x plus 6 quantity squared on the right side. So we have plus b over x plus 6 quantity squared. Alright, and then the rest of it is just like the last problem. So once you build them to a common denominator, what do you do next? Well, because they all have the same denominator, you can multiply both sides by that denominator, and that just means you cross out all the denominators. Okay, so all of these just cross out because they're all the same. Alright, so that actually gives us no more fractions, which is nice. So we have x plus 7 equals a times the quantity x plus 6 plus b on the right side. Okay, and then just like in the last problem, we're going to go ahead and distribute the a. We don't need to distribute a b here because it was just b times 1, which is b. But here we do need to distribute the a. So let's go ahead and do that. Okay, so we get x plus 7 equals a x plus 6a plus b. X plus 7 equals ax plus 6a plus b. And then just like in the last problem, we're going to go ahead and equate the powers. So we're going to equate the coefficients of like powers. So here the powers are the x's and then the constants. Alright, so equating the x's, here the coefficient is 1. So we have 1x equals ax. But remember, we're just equating the coefficients, so the numbers in front. And a is considered a number because it's an unknown, it's not a variable. Okay, so what we have here is our first equation is going to be 1 equals a. That's just equating the coefficients of the x's. Okay, so we have 1 equals a. And then here in green, I'm going to highlight the other coefficients. So for the other coefficients, we have 7 equals 6a plus b. 7 equals 6a plus b. And I know those are all like powers because none of those have an x, so they're all constants. I know it's hard to think of a and b as being constants, but they are actually going to be constants at the end, because right now they're unknown, but at the end when you solve for them, they're always going to be a number, which is a constant. Okay, so that's why we're allowed to do that. Okay, so what we have here is 1 equals a, and then 7 equals 6a plus b. And then to solve this system, I'm going to solve this one by substitution because the top equation is already solved for a, which makes it a lot easier. Okay, so looking at the top equation, that one's already solved for a. So we already know a equals 1. And then if we plug in a equals 1 into the bottom equation, we can solve for b. So that bottom equation is now going to become 7 equals 6 times 1 plus b. Okay, 7 equals 6 times 1 plus b. And 6 times 1 is 6, and then if we subtract 6 from both sides, we actually get 7 minus 6 is 1, so we get b equals 1. So we know a equals 1 and b equals 1. And of course the numbers won't always be this clean, but we got lucky on this problem that the numbers just kind of worked out for us. Okay, so now we can actually plug these back in into our original equation on the right side up here. So this was our original equation. Remember, I multiplied by x plus 6, but those weren't included in the original equation. So our original equation was this here. So x plus 7 over x plus 6 quantity squared equals a over x plus 6 plus b over x plus 6 quantity squared. So if we go ahead and just plug in a and b here, we know they're both 1 on this problem. So we're going to get 1 over x plus 6 plus 1 over x plus 6 quantity squared. Okay, 1 over x plus 6 plus 1 over x plus 6 quantity squared. And that pretty well takes care of it. Right, so that's going to be our answer. And I know with that one, because they both ended up being 1, you might think, well, I probably could have guessed that. And actually, that's another way of doing these problems, is right at the beginning, once you have it in this form where you have your 2 unknowns, or in the case of harder problems, you might have 3 or 4 unknowns, A, B, C, D, whatever. Sometimes you are able to actually guess them. But me personally, just looking at this, I might not be able to guess it as easily. But once you got down further here, you might have been able to guess it. Like from here on, you might have been able to guess what everything was. Okay? But yeah, that is our partial fraction decomposition. Now, you might be wondering, well, how is this equal to that? How do we know it's equal to what we originally got? Well, you can check these if you want. I didn't bother to check the first one, but you can check them. And the way you check them is basically you take your answer here and you build them to a common denominator, and then you add on the top, and then you make sure you get the original fraction. So I think I'm just going to do it for the second problem, the one that we just did, just to show you that. Okay, so that was up here. So you do not have to check them. I'm not requiring anyone to check these. But if you want to check them, it's not so bad. Basically, you check by building to a common denominator. Okay, so build to a common denominator is how you check. And then basically you're going to add and then see if you get the original fraction. So it's actually very easy to check. So like with this one we did here, if we want to check it, we start on the right side. So we have 1 over x plus 6 plus 1 over x plus 6 quantity squared. Okay, and to build it to a common denominator, I just multiply the first one by x plus 6 on the top and the bottom. Okay, so you build them to a common denominator like that, and then you add or subtract based on whether it's a plus or a minus. This one was a plus. Okay, so you build to a common denominator, then add or subtract. And if you get the original single fraction that you started with, that means you did it correctly. So like here, what do we get? Well, now that they have the same denominator, on the top we're going to have x plus 6 plus 1 all over the denominator, which is x plus 6 quantity squared. And x plus 6 plus 1 is x plus 7. So we get x plus 7 over x plus 6 quantity squared. And as you probably remember, that was actually what we started with. That was the fraction that we started with here. X plus 7 over x plus 6 quantity squared. And that right there is just awesome. That's what we started with, and it's really not too bad to check. So this checks out. Okay, so as long as you end up with the original fraction you started with, you're good. Okay, and then let's see, for your homework, we've kind of already talked about how you need a factor, so I think you don't need another example. So I think we're good for this video. And then in my next video, I'm going to be talking about actually, first of all, doing the partial fraction decomposition, and then using that to integrate, which actually isn't that hard, as you will see in the next video. Thanks for watching.